Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 10, Lesson 4 on graphs of polynomial functions. Make sure to have your graphing calculator today because we're going to see a lot of fun and cool graphs of polynomial functions. Let's jump right into it. Here we go. So, cubic polynomials. Polynomial functions have graphs that become increasingly complex as their degree increases. Remember, the degree of a polynomial is the highest power that the polynomial has. You've already studied quadratic polynomials. Those are the ones that have a degree of 2, right? Parabolas. And they're more interesting than lines, right? But you know, they're kind of an arch, either one that points down or points up, depending on whether the leading coefficient is negative, pointing down, or positive, pointing up. We're going to look at cubic polynomials. Those are the ones that have degrees of 3, and quartic polynomials, those are of degree of 4 in this lesson, and then we'll generalize to all polynomials from those two, and really kind of from quadratics as well. So let's take a look at exercise number 1. 3 cubic polynomial functions are shown graphed below to illustrate their behavior. All right, so I'm not going to read off the formulas. There are just 3 of them, right? We've got their behaviors, and they're kind of cool, right? I mean, they're definitely more complicated than a quadratic, certainly more complicated than a linear, okay? Now, what we're going to do in letter A, right, we're going to fill the table in below for the 3 functions. So what I want you to do for each function is I want you to give me the value of its leading coefficient. I want you to tell me the number of real zeros it has. Those are the same as the x-intercepts, so just circle them on the graph. I want you to count the number of turning points that they have, all right, and then I want you to tell me about their end behavior. So as x heads off to the right forever, where's the function headed towards? And as x heads towards the left forever, what is the function heading towards? So this should be pretty quick and easy. Why don't you go ahead and take a few minutes to fill out this table? All right, so let me just kind of bring it up here so that we can kind of see f of x real quick, right? F of x, simple enough. I have all these written in standard form, so it's simple enough. For the leading coefficient of f of x, I have 1.5, right? It's got 1, 2, 3 zeros. All right, the number of turning points it has, maybe I'll put those in a different color. Right, it's got a turning point here and a turning point there. It's got 2 turning points. Go back to blue. And now let's see, as x heads towards infinity, this thing is heading towards infinity. And as x heads towards negative infinity, it's heading down towards negative infinity. All right, so simple enough, right? Leading coefficient of 1.5, it's got 3 real zeros, it's got 2 turning points. As x is heading this direction, right, it's heading up towards infinity. As x heads towards this direction, it's heading down towards negative infinity. Now, real quick reminder of something that we saw in our last lesson, right? The long-run behavior of any polynomial is always dictated by a power function of the highest term. So in other words, right, the long-run behavior of f of x is really just dictated by 1.5x cubed. The long-run behavior of g of x equals x cubed plus x plus 2 is just dictated by 1x cubed, and the long-run behavior of h of x equals negative 2x cubed, etc., is just dictated by the negative 2x cubed. So we can understand why it's heading up in this direction and down in that direction by simply looking at that particular term. Now let's fill in the rest of them. All right, so for g of x, right, the leading coefficient was equal to 1. Great. The number of zeros, well, there was just 1 of those. If you thought we were going to always get 3, definitely not. The thing's got no turning points whatsoever, right? The thing never peaks out and then goes back down. As x heads towards infinity, this thing is going towards infinity. And as x heads towards negative infinity, this thing's going down, right, to negative infinity. Let's see, for h of x, the graph on my sheet that's in purple, its leading coefficient is negative 2. The number of real zeros it has, 1, 2 of them, just 2 real zeros. The number of turning points it has, also 2, 1, 2. And as x heads towards infinity, this thing is headed towards negative infinity. And as x heads towards negative infinity, this thing is headed up towards positive infinity. Okay. Right, now this is kind of interesting because, quadratics, those with x squareds in them, are relatively complex. But cubics have even gotten more complicated, right? I mean, geez, just look at the number of zeros, right? A cubic could have 1 0, 2 zeros, 3 zeros, maybe even 0 zeros. We haven't even seen one of those yet, but possibly quadratics can have 0 zeros. In other words, quadratics can miss the x-axis entirely, right? It looks like a cubic could have 2 turning points, 0 turning points. Maybe a cubic could have only 1 turning point. We'll have to see, all right? So let's start to answer some questions based on those 3 graphs. Letter B. Explain why a cubic polynomial function must have at least one zero that is a real number. In other words, I claim that no matter what I do, there is no way that I would ever have 0 zeros in terms of a cubic. Pause the video now and see if you can think about that. Well, it's kind of cool. You see, the ends of a cubic polynomial must point in opposite directions. You can kind of see that even in the last 2 columns, right? Here the right-hand side is pointing up towards infinity, the left-hand side is pointing down towards negative infinity, same here, and here it's reversed, all right? So since the endpoints must point in opposite directions based on the long-run behavior, then it must cross the x-axis at least once, right? So the ends must point in opposite directions, so it has to cross the x-axis at least once. Right? That's very different from a quadratic function, right? Think about a parabola. You can easily have parabolas, right, that miss the x-axis entirely, okay? But not a cubic, right? A cubic polynomial's long-run behavior is going to be dictated by that power function that includes an x cubed, and we know that all power functions that include an x cubed, the ends are going to point in opposite directions, and so it's got to cross the x-axis at least once. Let's take a look at letter C. Why is the end behavior different for h of x than it was for f of x and g of x? In other words, why is it that for f of x and g of x, right, we're going up, right, as x goes to positive infinity, and down as x goes to negative infinity, but for h of x, that trend is reversed? Why is that? Pause the video now and see if you can figure that out. It's pretty simple, right? Its leading coefficient is negative versus the leading coefficients of these two, which are positive. None of the other coefficients matter, not for the end behavior, right? Because the end behavior is always dictated by the highest powered term, right? And so because the leading coefficient here is negative and the leading coefficients here are positive, their end behaviors are opposite, right? So the leading coefficient, which is why that's an important term, by the way, the leading coefficient of f of x and g of x, leading coefficients of f of x and g of x are positive, whereas for h of x, it is negative. All right? And for long-run behavior, the only thing that matters is that highest powered term. And we looked at that in the last lesson. I'm hoping you were with me for the lesson on power functions and polynomials. Let's take a look at letter D. Clearly, a cubic polynomial can have no turning points, such as g of x, or two turning points, such as f of x and h of x. Can a cubic polynomial have only one turning point? Why or why not? All right, well, pause the video now and think about that for a moment. Could a cubic polynomial only have one turning point? The answer is most certainly no, and the reason why is if it did, its ends would point in the same direction. But cubic polynomials will always have ends that point in opposite directions. So no. If it did, its ends would point in the same direction, but for an odd degree polynomial, or polynomial, that would be great. A polynomial, they must point in opposite directions. Whew. Awesome. Think about how much richer, more complex, and interesting cubic functions are than even just one level below a quadratic function, right? Pretty much all quadratics sort of look the same, right? Parabolas kind of all look the same. They might be fatter, they might be thinner, they might point up, they might point down, but they kind of all look the same. On the other hand, cubics, right? You can have a cubic that's got like 3 zeros, 2 turning points, 1 0, no turning points, 2 zeros, 2 turning points. There's a lot going on with cubics. All right, and if you think cubics are fun, let's take a look at quartic polynomials. Exercise number 2. The quartic polynomial f of x equals x to the fourth plus x cubed minus 28x squared plus 20x plus 48 is shown graphed below. My goodness. Letter A. Why do the ends of this polynomial point in the same direction compared to the cubic polynomials that pointed in opposite directions? All right, well, this one's pretty easy. I think we pretty much just covered it in a certain sense. Pause the video now and tell me what you think. Because it's got an even degree, right? Again, it's all dictated, those long-run behaviors, all dictated by that highest power term because its degree is even. Man, I don't know why, but the red is driving me nuts today. Because its degree is even, right? And again, we should feel comfortable with why y equals x to the fourth, just that power function, right? Why its ends point in the same direction. And then what we saw in our last lesson was that the long-run behavior of a polynomial is going to be dictated by its highest powered term. So if the highest powered term is even, the two ends point in the same direction, and if it's odd, the two ends point in opposite directions. All right, letter B. Suggest a transformation of this function that would cause the ends to point downward, but would leave the zeros unchanged. All right, this is easy enough. What would you do to get this thing to look basically identical, right? Have exactly the same zeros, but have the ends point down instead of up. Pause the video now. Well, I'd reflect it across the x-axis, right? Reflect across the x-axis. And of course, how would you reflect across the x-axis? Well, you'd multiply the whole function by -1. So if I took this, y equals negative x to the fourth minus x cubed plus 28x squared minus 20x minus 48, right? If I took the whole thing and multiplied it by -1, right? All of this is just negative f of x, then all of a sudden the ends would point down. And again, that's just due to the fact that now the leading coefficient is negative instead of positive. All right, letter C. Circle the 4 real zeros this function has. List them below. All right, that's simple enough. Pause the video now, circle the 4 real zeros this function has, and list them below. All right, maybe I'll circle them in red just to have a nice color contrast with what's kind of going on up there already. Hand keeps getting in my way. Here's 1 at -6, 1 at -1, 1 at +2, and 1 at +4. So x equals -6, -1, +2, and +4. Awesome. Let's take a look at one last little piece. Letter D. Explain how vertically shifting this function can produce a quartic with no real zeros at all. So remember, we just saw a cubic has to have at least one real zero, but I claim that you could just vertically shift this thing and have no real zeros at all. Pause the video now and think about that a bit. Well, I don't exactly know what the minimum value of this function is, but it's around -300, right? So y min is approximately -300. So if you simply added, right, just added a constant onto this function that was greater than 300, it would shift the whole thing up so you got something that looked like that. And you would now have no real zeros, but you'd still have a quartic, right? You'd still have a quartic, so you'd have x to the 4th, plus x cubed minus 28x squared plus 20x plus, let's say, 348, right? So if I simply shift upwards by 300 or more units, the graph would no longer intersect the x-axis. Now, side note, if we shifted it up exactly whatever that minimum was, right? So that point was just touching the x-axis, we could get just 1 0, right? If we shifted it up just enough, so maybe this portion was touching the x-axis, we could get exactly 2 zeros, right? We could actually shift it in a variety of ways to get 1 0, 2 zeros, 3 zeros, or leave it alone where we have 4 zeros. We could even shift it down some, right? Moving this peak below the x-axis, right? Then it would just have 2 zeros there. All right, so it's kind of cool because quartics, right, can have all sorts of different types of zeros. Let's take a look at exercise number 3. The function y equals -2x to the 4th plus 16x cubed minus 48x squared plus 64x plus 68 is shown graphed. Letter A. Why does this quartic's ends point down instead of up like the quartic in exercise number 2? This should be pretty obvious. Pause the video now and go ahead and let me know. It's all about that leading coefficient, right? The leading coefficient is negative. The leading coefficient is negative, right? The long-run behavior of this particular polynomial is all dictated by that power function. And that power function, right, would have ends that point downward, both ends that point downward, because it's got an even power and the coefficient is negative. Letter B. This quartic has 1 turning point. The quartic in exercise number 2 had 3 turning points. Why can a quartic not have exactly 2 turning points? Also cool. Pause the video now and see if you can explain to me why a quartic, a fourth degree polynomial, could never have exactly 2 turning points. Well, let's try to draw it. Maybe, okay, 1 turning point, 2 turning points. How about 1 turning point, 2 turning points? Well, if it had exactly 2 turning points, its ends would point in the opposite direction. But a quartic must have ends that point in the same direction. If it did, the ends would point in opposite directions. Even powered polynomials have ends that point, that point in the same direction. Rogue board. It's rogue. It's going rogue on me. All right. Kind of great, right? Okay, so let's try to summarize this in exercise number 4. Fill in the following about a general polynomial function. All right, so what I'd like you to do is, given what we've just seen, and you can even bring in quadratic polynomials if you want, things that have an x squared in them, okay? So think about things with x squareds, then x cubes, then x to the 4th, and try to fill in each one of these so that they make some sense. Pause the video now, try to fill in each one of them, and then we'll go through them. All right, the maximum number of real zeros it can have is equal to its degree. Now, if you said is equal to its highest power, that's awesome too, okay? So a quadratic, an x squared, the maximum number of real zeros it can have is 2. A cubic, 3. A quartic, 4. All right, letter B. The maximum number of turning points it can have is equal to, well, a quadratic can have and must have 1. A cubic could have up to 2. And a quartic could have up to 3. So the maximum number of turning points it can have is equal to 1 less than its degree. And that's the maximum, because again, we saw a cubic that had 0 turning points, right? And we saw a quartic that had 1 turning point, okay? So that's just the maximum number, not the exact number. Letter C. Its ends will point in the same direction if its degree is even. All right, and easy enough, its ends will point in opposite direction if its degree is odd. Okay. So even though the behavior of polynomials becomes more and more complex as the degree goes up, we can see some general trends, most of which are summarized in exercise number 4. All right, so let's kind of wrap this up. So today was probably the first time you'd really ever examined graphs of cubic and quartic polynomials. You might have looked at them a little bit in Algebra 1, but probably not a ton, right? In here, we saw a lot of cool trends, all of which were pretty much summarized there in exercise number 4, right? One of which, hugely important, the maximum number of zeros that any polynomial function can have is equal to its degree. Again, the maximum number. We also did see that any odd-powered polynomial will have at least 1 zero, right? And that's because the ends of an odd-powered polynomial point in opposite direction. An even-powered polynomial, that can definitely have no zeros at all. Because those ends point in the same direction, we can sort of vertically shift that thing one way or another so it completely misses the x-axis. Turning points are also important, but they're a little bit more complicated. The maximum number of turning points that any polynomial can have will always be one less than the degree of the polynomial. All right? And again, you can think about that in terms of the end behavior of the polynomial. Okay, so we're going to work more with polynomials in our next lesson and how to form their equations if we know what their zeros are. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.